On the proper treatment of connectionism. Paul Smolensky, Department of Computer Science and Institute of Cognitive Science. University of Colorado, Boulder, Colorado 80309-0430. Abstract: a set of hypotheses I formulated for a connectionist approach to cognitive modeling. These hypotheses are shown to be incompatible with the hypotheses underlying traditional cognitive models. The connectionist models considered are massively parallel numerical computational systems that are a kind of continuous dynamical system. The numerical variables in the system correspond semantically to fine-grained features below the level of the concepts cons.easily used to describe the task domain. The level of analysis is intermediate between those of symbolic cognitive models and neural models. The explanations of behavior provided are like those traditional in the physical sciences, unlike the explanations provided by symbolic models. Higher-level analyses of these connectionist models reveal subtle relations to symbolic models. Parallel connectionist memory and linguistic processes are hypothesized to give rise to processes that are describable at a higher level as sequential rule application. At the lower level, computation has the character of massively parallel satisfaction of soft numerical constraints. At the higher level, this can lead to competence characterizable by hard rules. Performance will typically deviate from this competence since behavior is achieved not by interpreting hard rules but by satisfying soft constraints. The result is a picture in which traditional and connectionist theoretical constructs collaborate intimately to provide an understanding of cognition. Paul Smolensky is a highly influential cognitive scientist best known for co-developing optimality theory in linguistics with Alan Prince, a framework that explains linguistic patterns through the interaction of ranked, violable constraints. His work extensively explores the connectionist approach to cognition, aiming to bridge the gap between continuous neural processes and discrete symbolic representations through models like harmonic grammar, tensor product representations (TPRs), and the integrated connectionist symbolic ICS cognitive architecture, ultimately seeking to understand how the brain implements symbolic thought. Paul Smolensky earned his bachelor's degree in physics from Harvard University in 1976. He continued his studies at Indiana University, receiving a master's degree in physics in 1977 and a PhD in mathematical physics in 1981. After his doctoral studies, he became a postdoctoral researcher and research professor, becoming a founding member of the Parallel Distributed Processing Research Group at the University of California at San Diego, where he collaborated with figures like Geoffrey Hinton, David Rumelhart, and James McClelland. This early work laid the groundwork for his significant contributions to neural networks and cognitive science. Paul Smolensky's foundational work in the mid-1980s centered on establishing robust connectionist frameworks and introducing innovative representational schemes. His seminal 1987 paper, On the Proper Treatment of Connectionism in Behavioral and Brain Sciences, served as a critical manifesto for the connectionist program in cognitive science. It eloquently argued that while high-level cognitive processes might manifest symbolically, their underlying implementation in the brain is inherently subsymbolic and continuous. This paper introduced the concept of harmony as a guiding principle, suggesting that connectionist networks strive towards states of maximal harmony, a notion that would permeate his subsequent work. Simultaneously, starting with initial work in 1986 and detailed in a 1990 artificial intelligence paper, Smolensky developed tensor product representations (TPRs). This groundbreaking mechanism demonstrated how connectionist networks could encode and manipulate complex symbolic structures. TPRs achieve this by representing symbolic bindings like agent and action as outer products of feature vectors, which are then summed to form a single, distributed vector. This provided a crucial answer to criticisms that connectionist models lacked the capacity for systematicity and compositionality inherent in human cognition. Building upon his connectionist foundations, Smolensky introduced harmonic grammar in 1990, in collaboration with G. Legendre and Y. Mayata. This formal linguistic theory, detailed in their paper Harmonic Grammar, a formal multi-level connectionist theory of linguistic well-formedness, theoretical foundations, represented a significant departure from traditional rule-based grammars. Instead of prescribing strict rules, harmonic grammar evaluates the well-formedness of linguistic structures such as phonological forms or syntactic constructions by assigning them a numerical harmony score. This score is inversely related to the degree to which a structure violates a set of weighted constraints. The most well-formed, or grammatical, output is the one that achieves the highest harmony score. This framework's emphasis on weighted, violable constraints directly foreshadowed his most famous contribution. In a collaboration that would profoundly reshape the field of linguistics, Paul Smolensky, with Alan Prince, co-developed optimality theory (OT). Though widely circulated as a manuscript in 1993, the full book, Optimality Theory, Constraint Interaction in Generative Grammar, was formally published in 2004. OT posits that linguistic forms like the specific pronunciation of a word or the syntactic structure of a sentence are not generated by sequential rules but are instead selected from a set of possible candidates. This selection is based on how well each candidate satisfies a universal set of constraints. Crucially, these constraints are not absolute but are violable and are organized into a strict ranked hierarchy that varies from language to language. The optimal output for a given input is the candidate that best satisfies the highest ranked constraints, even if this requires violating lower ranked ones. This revolutionary framework provided a powerful new way to explain typological variation across languages and offered significant insights into language acquisition and processing, becoming a dominant paradigm in phonology and exerting considerable influence across other linguistic domains. Smolensky's ambition to create a unified theory of cognition culminated in the harmonic mind, from neural computation to optimality theoretic grammar, a 2-volume work co-authored with Geraldine Legendre and published in 2006. This magnum opus articulates the integrated connectionist symbolic ICS cognitive architecture, which stands as a monumental effort to seamlessly integrate connectionist principles with symbolic representations. The ICS architecture demonstrates how a connectionist system, operating on continuous activations and guided by the principle of harmony maximization, can nonetheless exhibit behavior that is accurately described by high-level symbolic theories like optimality theory. Volume 1 delves into the intricate details of the ICS architecture itself, elucidating its computational mechanisms, while Volume 2 explores its extensive linguistic and philosophical implications, demonstrating its capacity to explain diverse phenomena in language acquisition, online processing, and cross-linguistic typology, solidifying the bridge between neural computation and symbolic thought. Smolensky, Paul, Goldrick, Matthew, Mathis, Donald 2014. Optimization and Quantization in Gradient Symbol Systems, a framework for integrating the continuous and the discrete in cognition. Cognitive Science. 38-6, 1102-1138. Cho, Pyong Wan, Goldrick, Matthew, Smolensky, Paul 2017. Incremental Parsing in a Continuous Dynamical System, Sentence Processing in Gradient Symbolic Computation. Linguistics Vanguard. 3-1. doi 10.1515 Lingvan 2016-0105. S2 SID 673621774. More recently, in 2018, Smolensky, along with P. Tupper and P. Cho, advanced his ICS framework by introducing gradient symbolic computation (GSC) in their paper Discrete Symbolic Optimization and Boltzmann Sampling by Continuous Neural Dynamics, Gradient Symbolic Computation. GSC further refines the understanding of how discrete symbolic structures can dynamically emerge from the continuous activity of a neural network. It offers a mathematically rigorous account of how a system with continuous, graded activations can progressively converge on an optimal, discrete symbolic interpretation. This framework uniquely accommodates blends of partially activated symbols and structures, providing a powerful mechanism to model ambiguity resolution and graded linguistic phenomena that are challenging for strictly discrete symbolic models. Smolensky, Paul, Rosen, Eric, Goldrich, Matthew 2020. Learning a Gradient Grammar of French Liaison. Proceedings of the 2019 Annual Meeting on Phonology. 8 doi 10.3765 amp v8 I 0.4680. In the rapidly evolving landscape of artificial intelligence, Paul Smolensky continues to apply his enduring insights into symbolic connectionist integration to contemporary large language models. His 2024 paper, Mechanisms of Symbol Processing for In-Context Learning in Transformer Networks, co-authored with R. Fernandez, Zhou, M. Opper, and J. Gao, investigates how modern transformer architectures achieve in-context learning. This research proposes that symbolic operations, often considered beyond the scope of neural networks, can arise from the transformer's attention mechanisms. The paper also introduces a high-level symbolic language, PSL, suggesting that symbolic programs could potentially be compiled into transformer networks to enhance their symbolic processing capabilities. Furthering this line of inquiry, his 2024 survey paper, Toward Compositional Behavior in Neural Models, a survey of current views, with K. McCurdy, P. Solos, R. Fernandez, and J. Gao, reflects on the persistent challenge of achieving robust compositional behavior in neural models. This work contributes to the ongoing debate about the strengths and limitations of current neural architectures in replicating the intricate, systematic, and compositional aspects of human cognition. Tensor product variable binding and the representation of symbolic structures in connectionist systems. Paul Smolensky. Abstract. A general method, the tensor product representation, is defined for the connectionist representation of value variable bindings. The technique is a formalization of the idea that a set of value variable pairs can be represented by accumulating activity in a collection of units, each of which computes the product of a feature of a variable and a feature of its value. The method allows the fully distributed representation of bindings and symbolic structures. Fully and partially localized special cases of the tensor product representation reduce to existing cases of connectionist representations of structured data. The representation rests on a principled analysis of structure, it saturates gracefully as larger structures are represented, it permits recursive construction of complex representations from simpler ones, it respects the independence of the capacities to generate and maintain multiple bindings in parallel. It extends naturally to continuous structures and continuous representational patterns, it permits values to also serve as variables, and it enables analysis of the interference of symbolic structures stored in associative memories. It has also served as the basis for working connectionist models of high-level cognitive tasks. References: Prince, Alan, Smolensky, Paul 2002. Optimality Theory, Constrained Interaction in Generative Grammar Report. Rutgers University. doi 10.7282 T34M92 MV. Updated version of July 1993 report. Legendre, Geraldine, Grimshaw, Jane, Viner, Sten, eds. 2001. Optimality Theoretic Syntax. MIT Press. ISBN 978-0-262-62138-0. Legendre, Geraldine, Putnam, Michael T. de Swart, Henriette, Zarukian, Aaron, eds. 2016. Optimality Theoretic Syntax, Semantics, and Pragmatics, From Uni to Bidirectional Optimization. Oxford University Press. ISBN 978-0-19-875711-5. Smolensky, Paul. November 1990. Tensor Product Variable Binding and the Representation of Symbolic Structures in Connectionist Systems. Artificial Intelligence. 46 1-2, 159-216. doi 10.1016.000423702990007. M. Legendre, Geraldine, Mayata, Yoshiro, Smolensky, Paul. 1990. Harmonic Grammar, A Formal Multi-Level Connectionist Theory of Linguistic Well-Formedness, Theoretical Foundations PDF report. In Proceedings of the 12th Annual Conference of the Cognitive Science Society, pages 388 to 395. Cambridge, Ma, Lawrence Erlbaum. Report CUCS 465-90. Computer Science Department, University of Colorado at Boulder. Smolensky, Paul, Legendre, Geraldine. 2006. The Harmonic Mind, From Neural Computation to Optimality Theoretic Grammar. Volume 1, Cognitive Architecture. Cambridge, Ma, MIT Press. Smolensky, Paul, Legendre, Geraldine. 2006. The Harmonic Mind, From Neural Computation to Optimality Theoretic Grammar. Volume 2, Linguistic and Philosophical Implications. Cambridge, Ma, MIT Press. Smolensky, Paul, Goldrick, Matthew, Mathis, Donald. 2014. Optimization and Quantization in Gradient Symbol Systems, A Framework for Integrating the Continuous and the Discrete in Cognition. Cognitive Science. 38.6, 1102-1138. doi 10.1111 cogs.12047. PMID 238028007, via Rutgers Optimality Archive. Smolensky, Paul, Rosen, Eric, Goldrick, Matthew. 2020. Learning a Gradient Grammar of French Liaison. Proceedings of the 2019 Annual Meeting on Phonology. 8 doi 10.3765 amp v8 I 0.4680. Cho, Pai-Yong Wan, Goldrick, Matthew, Smolensky, Paul. 2017. Incremental Parsing in a Continuous Dynamical System, Sentence Processing in Gradient Symbolic Computation. Linguistics Vanguard. 3.1. doi 10.1515 Lingvan 2016-0105. S2 SID 673621774.